Unless you know what to look for, you might never notice a weld joining two rails on the railway. They don't look like much, but it takes skill, precision, and an incredibly powerful chemical reaction to form a welded joint. One misstep, and that weld could fail. This is aluminothermic welding, a reaction so intense it turns powders into molten metal in seconds. Each weld depends on a sequence of steps that ensures the track runs smooth, and it all starts long before the pour with how the rails line up. Before any heat, it starts with precision. You need to get it right from the very start, and that means aligning the ends of the two rails to be welded. There are two ways to do that: A-frames or simple wedges, which are packed under the rail. What's used often depends on the equipment available or the welding team's preference. Whatever the method, the goal is the same. Align the two rail ends so they create a smooth, continuous running surface once welded. The gap between the two ends, typically 25mm, is set using pre-measured spacers that match the welding portion's design. Then, vertical alignment. The running surfaces are set up with a small peak of 1.5mm over a meter to allow for both contraction and to avoid the final weld becoming dipped the train's wheels will run on. Lateral alignment. The gauge faces line up across the joint. Longitudinal alignment. There's no step or kink through the joint. Once locked in, it must not move. Grinding later can refine the surface profile, but it can't fix misalignments inside the weld. That's why this stage decides whether the finished joint runs smoothly or hammers under every wheel for the rest of its life. This video is sponsored by Pandrol, pioneers in rail welding innovation. For over a century, aluminothermic welding has joined the world's railway rails, and Pandrol's I+ Weld range is taking that process into the future. The products in the range take elements of the traditional processes and make them better. I+ Align automatic rail aligners achieve the perfect setup at the press of a button, replacing the A-frames and wedges we mentioned earlier. Then there are the I+ Seal self-sealing molds that remove the need for luting. You will see that managing heat is key to a good weld. Pandrol's I+ Heat fully automated preheater achieves the perfect rail end temperature prior to welding every time. After the weld is finished, the I+ Cool can be used to cool welds faster, all under complete control. The result? A faster, safer, and more consistent welding process, estimated to give up to 40% higher productivity, and full traceability of every weld through I+ Connect, Pandrol's digital data platform. Pandrol are changing welding, not just selling consumables, combining automation, data, and real-world practicality to make aluminothermic welding more intelligent, safer, and more efficient. Find out more about I+ Weld at pandrol.com/i-weld. With the alignment complete, the next requirement is containment. Before any molten metal is produced, the joint needs something to pour into. That containment comes from the mould fitted around the joint. The alignment is locked, and now a mould is fitted around that joint. This mould is refractory, meaning it's made from a heat-resistant material designed to withstand extremely high temperatures without breaking down or reacting with the molten steel. The mould sits tightly around the rail head, web, and foot, enclosing the gap between the two rail ends. Its internal shape mirrors the rail profile, defining the form the weld will take once the metal solidifies and is ground back. The mould performs three critical functions. First, it contains and directs the molten steel during the pour. Internal channels guide the metal into the joint from the bottom up, allowing air and slag to rise away from the running surface rather than becoming trapped inside the weld. Second, it creates a riser above the rail head. This acts as a reservoir, feeding more molten metal into the joint as it cools and shrinks, preventing voids and internal defects from forming in the load-bearing area. And third, it seals tightly around the rail. Any gaps would allow molten metal to run out or air to enter the mould, which can weaken the weld, distort its final shape, or starve the joint as the steel solidifies. Get the mould wrong, and even a perfect alignment and chemistry can't save the joint. Once a mould is fitted and sealed, the focus shifts to temperature, because the rail has to be prepared before any molten steel is introduced. Steel expands rapidly under heat, which means if it's hit with molten metal while cold, The temperature difference can cause cracking before the weld even forms. That's why welders preheat both rail ends to around 850 degrees before the pouring. They use a gas burner inserted into the top of the mould, using a specially designed nozzle that directs heat evenly around the rail head and web. Preheating continues for several minutes, depending on the outside temperature and the heating equipment being used. This preheating does three key things. It ensures the molten metal stays hot enough to bond with the rail ends, rather than cooling too quickly and failing to fuse properly. It removes moisture, mostly from the mould material, but also from the rail surface if the weather's damp. This reduces hydrogen that could cause cracking, known as hydrogen-induced cracking. Then, it prevents thermal shock within the rail itself by equalizing the temperature across the rail's cross-section, avoiding the sudden expansion and contraction that can distort or fracture the heat-affected zone. Think of it like easing metal into the heat rather than shocking it, letting the atoms expand gradually so the bond that follows is solid from the start. If you skip this step, the hidden cracks or poor fusion almost guarantee weld's early failure. This is where the science takes over. Inside the crucible, above the rail, sits a pre-packaged portion, a precisely measured mix of iron oxide and aluminium powder. This pre-packaged mix is known as a portion, a single-use charge engineered with the exact ratios of the materials needed for one weld. It doesn't react on its own, it needs a deliberate trigger. A small ignition charge, often a magnesium ribbon strip or electric igniter, depending on the system, is lit by the welder. That heat starts the aluminothermic reaction, a redox process where aluminium steals oxygen from iron oxide. This reaction reads as iron oxide plus aluminium produces iron, aluminium oxide, and heat. The aluminium is oxidized, forming aluminium oxide, while the iron oxide is reduced, releasing molten iron and an enormous amount of heat. Temperatures reach about 2,500 degrees, hot enough to liquefy iron instantly. Inside the crucible, two layers form. Molten iron sinks to the bottom. Aluminium oxide slag forms on the top. At the base of the crucible is a refractory plug, a heat-resistant barrier called the thimble in some systems that delays the pour. When the reaction reaches full temperature, the plug softens and melts, allowing the molten iron to drop down through the runner into the mould and between the preheated rails. As it flows in, it fuses with the rail ends, allowing limited diffusion of carbon and alloying elements to ensure metallurgical compatibility with the parent rail. The mould fills from the bottom up, forcing air and the slag up into the riser and preventing trapped gas or inclusions in the joint. Every portion is manufactured under controlled conditions, meaning that what happens next is predictable. That's the power of aluminothermic welding. It's a portable foundry chemistry refined for trackside use. After the aluminothermic reaction reaches full temperature, timing becomes everything. Once the reaction starts to run, welders don't interfere, but they do stay alert, monitoring the ignition, the duration of the reaction, and the way the molten steel flows into the mould. They're making sure the reaction runs for roughly the right amount of time before the pour begins. If the reaction ends too quickly or drags on too long, it usually means the portion hasn't burned as intended, which can reduce the weld's strength, disturb fusion, or alter the metal composition. A correct pour gives a steady, continuous flow of molten steel that fills the mould evenly, leaving clean slag at the top once solidified, ready to be removed. When it behaves as expected, it means the chemistry, timing, and setup have all done their job. Rail joints are crucial parts of the track, but they're not the only part. Every section of the track is made up of components that work to keep trains stable, moving, and secure. If you want a clearer picture of how it all fits together, I've put together an exclusive Track Components ID guide, a visual reference that helps you identify every key part, from clips and pads to insulators and base plates. It's free to download, and it's the easiest way to build confidence when talking track. Grab your copy using the link in the description or in the top right hand corner now. Once the pour is complete, the focus shifts from chemistry to metallurgy, how that molten steel solidifies into the finished joint. The weld is normally left to cool naturally, with gradual heat loss through the mould and into the surrounding areas. In very cold conditions, insulation might be used to avoid extremely rapid cooling. However, this is changing, with products being introduced to speed up weld cooling whilst ensuring it's done under control. The riser and any remaining slag are removed. Excess metal that was deliberately added during the pour to feed the weld as it's cooled, but now it's removed using a hydraulic trimmer. As the metal solidifies, its internal grain structure forms. Cool it too quickly and it turns hard and brittle. Cool too slowly and the grains become large and weak. The target is a fine perlitic structure, the same type found in most other railway steels, which gives strength, ductility and fatigue resistance. The weld is then ground back to the rail profile, restoring the running surfaces and gauge face so that train wheels pass smoothly over the joint without impact or load concentration. Finally, the weld is inspected, visually first, then sometimes by hardness or ultrasonic testing where required. That invisible microstructure decides whether a weld lasts months or decades. Aluminothermic welding might look like routine track work, but it's physics, chemistry, and precision engineering all combined. Alignment ensures the rails meet perfectly. Heating stabilizes the steel. The aluminothermic reaction produces molten metal that fuses into a joint. The refractory plug and mould control a pour, and cooling locks in the final structure of the material. Get them all right, and two separate rails become one continuous piece of track, strong enough to carry thousands of tons of train load day after day. That's what turns a brief burst of chemistry into a rail joint